Our next speakers are going to talk about sticking to the facts, a scientific study of static analysis tools. Chuck Willis and Chris Breton, all you.
Thank you very much. Good afternoon. Chuck and I, my name's Chris Breton, and to my right is Chuck Willis. And we have the unenviable position to standing between you and a night on the town in Las Vegas. So I hope that you'll find the information in this brief is interesting, and Chuck and I find it in presenting it. We're passionate about this topic of software assurance, and we hope that it's very positive to see that there is actually so many people here that hopefully share that passion. As I mentioned, my name is Chris Breton. I'm the director of something called the NSA Center for Assured Software, and so and we sponsored this work. So anyway, we'll be talking about a particular study that we did last year. In the context of today's discussion, this is kind of the format we're going to follow. I'm going to spend a few moments offering up a little bit of background and context for our work. I'm not going to spend a whole lot of time on that, just to give you that context. Chuck's going to come up and give all the technical details. He was our team lead on this activity, and so he's going to be really giving you most of what I call the real good information about how we tested these tools and this technology and some of the conclusions that we came to. So we'll be following this plan here. I'll be handling the first bullet, and Chuck will be up here for the rest of it. So first, a little bit about the Center for Assured Software. Our mission is to work with our client base, which is really the Department of Defense. And as our mission statement says, our job is to essentially influence the department to increase the software assurance posture of software that is deployed in military environments. And we do that in a number of ways. We assess technology, and we interact with specific clients on what we know about that technology. And we also work with policymakers and standards groups and the broader academic and business community to identify tools, techniques, and processes that work and help to increase that software assurance posture in a scalable way. And that's key, scalable way. There's lots of tools out there, and those of us in the formal methods world know that there's a lot of work that goes on in automation and to highly automate formal proofs of software. The issue for that type of technology that we continue to struggle with and have for years is the scalability of that. And as I don't have to tell this audience, the department, as well as the rest of the business community and the federal government, deploys an enormous amount of software. And we have to have tools and techniques and processes that scale. And so that's kind of what the Center for Assured Software is about. We look to be a center of excellence for our clients, a trusted third party to talk about that technology and to give advice and guidance on how to use that technology appropriately. So our focus area in the context of that technology, we would like, because of the scalability portion of our mission, we encourage the appropriate use of automation. And the key there is appropriate. Many of our clients, and I don't think they're any different than clients around the world, are looking for that silver bullet, if you will, to run their software through and to say, it is indeed secure, or I can trust this software to perform some function. The reality is that software assurance really begins back at the developer's desk, and that's conventional wisdom. There is no silver bullet, and that's part of the message that we take to our client base. Appropriate use of technology, we highly encourage. That helps the scalability. But to rely only on technology today, the state of the art doesn't really accommodate that. And so that's part of our message. Another part of our message in the context of scalability and what's available today is to look at the properties that's closest to execution. Okay, we see the little moniker up there, let the code speak. In the Department of Defense, and most of you are probably aware of this, a lot of our assurance cases are made through what's called certification and accreditation. a lot of analysis, design analysis, a lot of documentation review. It's a fairly bureaucratic process, and this is acknowledged in the department, and there's a lot of work going on to try to address that particular concern. What we're trying to get at in the context of our focus area is getting as close to the executable as possible, as is reasonable, to make assurance statements about arbitrary pieces of software. And so letting the code speak, i.e. input source code or executable content, and then coming up with some conclusions about that in a fast, scalable way is kind of a part of our mantra, if you will. So therefore, we spend a significant amount of time looking for new software assurance tools, techniques, and processes in the context of automation. And so that's kind of where we're going to talk about today. We do this in a number of different areas. Today is just, we're talking about is the results of just one study that we did. So before we get into Chuck giving you the details of that work, let's talk a little bit about how we're viewing static analysis. And this is just a quick slide to talk about how we define static analysis in the context of this study. I don't think it's overly controversial, but some things to note up there that it doesn't have, static analysis does not have to be done by a tool. However, people can do static analysis, and they do all the time. The issue there is scalability, and how do we scale that using automation techniques. Notion of static analysis down at the bottom, you can see it's also known as static code analysis, static program analysis, source code analysis. In our study, and I think more broadly, we're getting away from the term, I think, of source code analysis, and we're just talking about because there are tools and techniques out there that are able to look at executable content in a static way. And so our tool study actually didn't make a delineation between executable content and source. So we're just looking at it in the context of a static review of source or binary. A final slide before I turn it over to Chuck about the properties of static analysis and tools today and kind of the state-of-the-art technology. The idea is to automate. I've already talked a little bit about that. There are commercial and there are open source tools, and so we make some statements about that. We did have an open source tool or two in our study. A conclusion that Chuck will enforce with the methodology where we've used, as well as the conclusions. He'll talk about that they vary widely in capability and features. And so that's part of kind of what we're looking at to determine how they can bend these tools and how we can talk about them to our clients in a reasonable way. So with that, I'll turn the presentation over to Chuck, who's just going to talk about how our methodology as well as the general conclusions. And then we'll take some questions afterwards. And I promise Chuck will keep it within or before the time frame to let everybody get out and get started on the evening, because I know that's a real top priority. Thank you very much. We'll talk to you in a few moments.
Okay, thank you, Chris. So as Chris mentioned, I'm Chuck Willis. I work for Chris at the CAS. I also work for Mandiant. I'm a contractor, just full disclosure, I suppose. But I want to talk about a couple slides here that Chris forgot to cover, I suppose. So the benefits of static analysis tools. So Chris talked about what static analysis tools are, and this is why we're looking at these types of tools, because they can identify problems in software. They have issues that there are issues in the software, they can find them and report them to you, which obviously is something you want to do. They're good at finding certain types of issues. And importantly, the static analysis portion of it, meaning that they're analyzing the entirety of the code base, means that they're able to see all parts of the software. So it's not just executing certain code paths as you would get if you did dynamic analysis. This is looking at all different possible branches of every single part of the code. So it's and as we talked about earlier, they're automated, scalable, repeatable, allows you to basically cover a lot of code with a relatively small amount of manpower. And so that's kind of the tool aspect of it, as opposed to static analysis that's done by humans. And you can use it early and often because of that. But there are, of course, some limitations with static analysis tools, and that's just something that everyone, I think, recognizes, but we want to make sure that it's clear in our presentation here. Most do not report the good things in software. So basically, they're going to report bugs or vulnerabilities or whatever you want to call them in your software, and then you go fix a bunch of them, and then it's like, well, then do you really have any more assurance in the software is good? If you had one piece of software that had no vulnerabilities reported by the tool, another had a bunch of vulnerabilities, and then you fixed them, which one is better? They both now have no vulnerabilities being reported, but you don't have any positive kind of things to measure that way. So, but that's a limitation of kind of the current technology. Then there are, of course, if you've used any type of tool, honestly, not just static analysis tools, there are going to be false positives typically. They're going to be reporting some sort of flaw where that flaw doesn't actually exist. So you're going to have to kind of sort through those. You're also going to report some things potentially that you don't care about. So the static analysis tools report a wide variety of things, including things like code quality issues that you may or may not care about. So that's, some people kind of lump those in with false positives. In reality, it's kind of separate. But fortunately, all of the tools that we've looked at can be tuned in various ways in order to reduce that. But you have to kind of consider that as part of the overall kind of package with static analysis tools. And you also cannot always definitively report issues in static analysis. So what static analysis tools are trying to do is in some way analogous to the halting problem in computer science. So they're kind of trying to do fundamentally unsolvable problems is what they're trying to solve. So they end up using heuristics, and so they're going to have some variance in one way or the other. They're either going to miss things or report false positives. And in some cases, it's maybe a false positive, maybe it's really there. Some human's going to have to look at it in order to kind of verify the issue. So it's not a completely automated process in some cases, depending on the flaw type that you're looking at. And then more specifically, kind of getting to our study here, static analysis tools do not cover all the flaw types in the world. I mean, it'd be great if they did, but unfortunately they don't. And they're in particular much better at implementation flaws, so more like a bug as opposed to a design issue or some sort of kind of fundamental architecture problem in an application. And we do say, you do have to be a little bit wary that vendors will sometimes say, oh, well, we report buffer overflows, when what they mean is they report at least one kind of buffer overflow, whereas there are very many different types of buffer overflows. And so you just need to kind of take some of that stuff with a grain of salt as far as looking at the overall picture and not just looking at kind of the spec sheet that vendors provide to you. And as I don't know if we mentioned earlier, but they do miss things. Like I said, the tools don't report every type of issue. So even flaw types they cover, they don't report every single type of buffer overflow. They might just report certain ones. You may miss things, and therefore you have this false sense of security because I ran the tool, it didn't report anything. Therefore, I'm going to go ahead and think that my software is okay, but it's really got problems. And then, so this is all detailed really in our next section when we talk about the tool study specifically and our conclusions in that. But I just wanted to kind of give a framework for why we're doing all this. So now let's talk in detail about the study. Well, I have slides here that talk about kind of the framework of the study and how we did things. I'm going to try to go through those relatively fast because that is also detailed in the white paper that we provided on the CD, and I think it's on the BlackHat website, or it will be soon. So you can look at that for more detail on that. The conclusions that we talk about at the end is just in the presentation. So, and as Chris mentioned, at the end we'll take questions kind of offline, and we'll be happy to talk about this stuff for as long as you guys want to stick around. So the purpose of the studies that the CAS has done, the most recent one is in 2010, is we want to study the capability of commercial and open source tools in the static analysis realm, and specifically looking at C, C++, and Java at this time. We may expand into other languages in the future, but not in 2011. We want to know specifically where are they strong and where do they maybe have false positives. What do they find? What do they miss? Where do they have false positives is kind of the gist of what it is. And also looking at maybe how you can combine tools, so you can create a meta tool that uses the strengths of different tools together to give you much better coverage, perhaps. What we're not trying to do is to choose a best tool or even to rank tools overall in any way. So we look at individual areas, which we'll detail later, and that's kind of how we look at things. We don't look at the overall picture. And we also very explicitly say that we only are looking at results. And so the methodology focuses on what are the results from the tool, what things are they able to find, what do they miss, as I mentioned earlier. We're not looking at cost or performance or customization or reporting capabilities or a lot of other things that you really need to consider when you're purchasing a static analysis tool. But what we do feel is that a lot of those other things are both subjective, and we wanted to keep our study very objective, but they're also kind of easy to see. So if you look at a static analysis tool, you're going to clearly know what it costs because the vendor's going to give you a proposal. You're going to be able to see the performance because you're going to run it on some test code, and you're going to be able to know kind of the ease of use and customization and reporting. So we wanted to try to quantify what was very hard for people to see, which is, how good are the results from the tools. But like we certainly don't think that this would be like the only factor that you would use. So we generally, when we talk to our clients, we'll say in the areas that this client is concerned about, we think that these couple tools are the kind of the recommended ones that we would use on kind of the short list, and then that they would choose among those based on these other factors that are important. But I will, of course, caveat it with saying that you could have the tool that has the greatest user interface and the prettiest reports and great customization, but if it doesn't find the flaws, then it doesn't find the flaws. There's no point in deploying that tool. So we feel that the results are a very important factor, but they are only one factor to be used in choosing a tool. So the tools that we studied, unfortunately, we can't give you the names. You could probably guess some of these based on the categorized, but yeah, that's okay. We expected that. But and our abstract did explicitly say anonymized results. But we do have some results at the end that show kind of the aggregate data. But the point here at this part of the talk is really to talk about the methodology that we use and how this works. But you can, like I said, probably guess what some of these tools are based on just the languages that they cover and the open source or commercial nature. So it ends up being 7 tools in each category, each language family. We cover C and C++ as one language family, we call it, even though they are separate languages. All the tools cover both of them. And so the overall methodology, we'll go through quickly, and then we detail some of these steps later. We analyze the test cases. So the test cases are these pieces of code that we've created with each tool in its default configuration. So that's an important caveat in our methodology at this time anyway, that we didn't try to tune the tools in any way to the test cases. We didn't annotate the test cases as you maybe would if you were have a code base that you were scanning with the tool all the time. We also didn't mess with the kind of rule set that was enabled or disabled in the tool. So there could be cases where tools just have rules that were off by default, and therefore the tool missed things that it could have found if you had used a different configuration. So we're going to be addressing that in 2011. But for 2010, the study was we used each tool in the default configuration. So once you had analyzed the code, every tool spits out its own output format. Most of them are XML based in some way, but they have their own schemas. We converted all of those using XSLs into a comma separated value format, so it's basically a spreadsheet. And then once we had it in that kind of standard format, then we were able to use kind of common tools beyond that point to go through the scoring is what we call basically marking true positive and false positives. And then once you had those results, grouping them into some kind of countable number of things you could talk about, and then generating statistics. And so, like I said, we'll go over these in more detail. You might be familiar with NIST, the National Institute of Standards and Technology. They have a project called SATE, the Static Analysis Tool Exposition. And so they do, in some ways, similar things to what we're doing in the sense of they are analyzing, or they call it an exposition. So they're kind of trying to showcase the capabilities of different static analysis tools. But we highlight here some differences between us and what they're doing. And they're actually looking at maybe incorporating some of our ideas into their next run as well. But the gist is we feel our work is complementary to theirs. So they're doing things a little bit differently than us, and I think there's advantages to each approach. And so we don't feel that we're like somehow better than them or somehow doing something that they're not doing. We just think it's a different approach. In particular, they use basically open source projects to scan, the tools scan. So there's limitations there because they don't represent all the different possible flaw types that would be in there, whereas our approach of using synthetic code, we do have at least, we won't say our test cases are perfect, but we have a pretty wide breadth of flaw types that we cover. So the test cases I mentioned earlier, so our test cases are these little pieces of artificial code that we've created explicitly for testing software analysis tools. So as Chris mentioned earlier, we covered both binary analysis and static analysis and source code analysis tools in our study. You could even potentially use these test cases with dynamic analysis tools if you wanted to or whatnot. But they're explicitly created for testing tools, so that they're artificial in that sense. Every test case has exactly one what we call target flaw. So that's we'll have an example here in a second of what that's supposed to be. And then you'll have one or more kind of constructs that look similar to the flaw, but they have basically been fixed. So they, as much as possible, kind of do the same function as the flawed code, and they have the same kind of control flow and that sort of thing. So really, basically, those are primarily there as opportunities for tools to report false positives. So we want to know, to the bads is what gives us an opportunity to see what the tool report. The good gets us an opportunity to see what the tool has problems with as far as reporting false positives. And as we mentioned, C, C++, and Java. So here's an example of a test case. So let's go through real quickly. So we use CWE, which is MITRE's common weakness enumeration, as the kind of standard naming convention for us. So this is CWE 134, which is an uncontrolled format string vulnerability. You'll see that this is a function basically within that, so I had to wrap the line because it wouldn't fit. But we had these big, ugly function names because we have to parse things later. And we also have scoping issues where, because C doesn't have namespaces or anything we can use, so we have to basically have a fully qualified function name here so we don't have conflicts. But then this is explicitly the bad code, which my laser pointer isn't working on, but I can probably mouse over it perhaps, or I'll just point to it. Bad code. And then down here we have the scanf, where you're basically reading in data from the console, and then the flaw is really down here in the printf section, where you're basically taking that data you just read from the console and putting it into a printf function without any sort of format specifier. So that would be perfectly fine as long as the buffer doesn't contain %s's or %n's or anything, but if it did, then you could potentially have at least crashes, if not sometimes arbitrary code execution. This is also kind of assuming that the binary would be running as like set UID or something, because it's not really very helpful to do this against your own process. But if it's a process that's running with elevated privileges, then you could use this to exploit it. So that's what the flaw looks like, and we in this example have this nice flaw comment above it. We tried to put those in, but won't guarantee they're in all of our test cases. The test cases are publicly available. I'll give you the link here in a little bit so you can go look at all these yourself. I will also say this is kind of a notional test case. This is from an earlier version of our test cases. The modern one is a little bit more complicated because we have variants for various different data types and things like that, but it gives you the idea of kind of what we're trying to do. This is the good code that's basically this statically scoped, so we don't have to have the big ugly name, but this is the version that fixes the problem. So the exact same data coming in, the scanf into the buffer, but the fix is we're putting out the %s here in front of the printf so that we know that if you could put all the %s's you wanted into the buffer, it's not going to cause any, not going to get rendered as a format string. So that's basically what our test cases look like, and so you just repeat that a couple tens of thousands of times and you've got them all. So the advantages of the test cases, as I mentioned, it's a little bit of a different approach than, for example, SADA is using, is we've got a lot of control because we're generating these things artificially. So we can control the breadth of flaws that we cover, all the non-flaws that we cover. That way we can study the full range of tools capabilities, so we don't have to worry about kind of trying to assemble various code bases, and are we still ever going to be able to cover all the flaw types that these tools cover. Or even tools that, maybe some of them, none of the tools cover currently, but we would like them to cover. So that's kind of part of our notion here too, is we wanted to be able to provide a nice wide suite of test cases that vendors could use to potentially add additional test cases, or maybe people could go off and write custom rules for tools or whatnot. We also have control over exactly where the flaws and non-flaws occur, as I showed you earlier in those function names, and that gets into our scoring later, so we can simplify that process. We don't have to worry about knowing exactly which line the flaw actually exists on. We just have to know the function name that it appears in. And we can then take the constructs that we have here. So this is basically a source and a sink. This scanf is a source of data. This printf is a sink of data, so where the data ends up. You can take those two pieces there and put them into all sorts of data and control flow variants. And so that's what we have, a custom engine that we have that generates those. So you can kind of provide these template files and then kind of tell it what to put into the templates, and then it generates a whole bunch of them. So we have a whole bunch of test cases, but very few of them were manually generated. Most of them were automatically generated through that templating system. But we will admit that there are limitations to our test suite. They are simpler than natural code, so there are some, like I said, data and control flow complexities, but even the most complex test case is only a handful of files long as far as the graph. There's not really a lot of control flow complexity, so there are limitations there. We do feel, though, that so tools may have better results on our test cases maybe than they would have on real code, but all the tools are still analyzing the same code. We use the exact same test suite for all the tools, so you're at least comparing apples to apples as far as comparing the tools against one another, as opposed to if you were doing it in like I said, trying to really predict exactly how the tools are going to behave on real code, because every real code base is going to be differently anyway, so you don't really know how tools are going to act on any specific code base. All the flaws are represented equally in our test suite, so the most common type of buffer overflow in the world appears exactly once in one test case, and the rarest kind of buffer overflow in the world is probably not in our test suite, but the second most rarest one maybe we've got at the end of our test suite, and we've got that's also one, and it gets counted basically the same as the most common type of buffer overflow. So we've among different flaw types, we do handle this a little bit, but within the same kind of type of flaw, like I said, buffer handling issues or pointer issues or whatever, that is kind of a problem, a limitation that we have. We would like to fix this, but we just don't know how we could do it, because you'd have to come up with some notion of how do you measure how common each specific flaw type is. And we might be able to do that at like the CWE level, but probably not down to the variant, especially when you start looking at data control flow variants. And so we may try to fix this. We're actually looking at what MITRE is working on with their common weakness scoring system as well, that maybe they're going to have some information that we can use to help do some sort of weighting. In general, we prefer to not come up with any sort of weighting ourselves, because then we have to defend it. So we'll happily use what someone else comes up with, and then we can point to them if people have issues with it. And the ratio of flaws and non-flaws is much different in our test suite than in real code. So in real code, you would hope that flaws are relatively uncommon and that non-flaws are more common. I mean, there's still a lot of flaws per line of code, it seems like, from the talks I've heard even today. But in natural code, yeah, you're going to have more non-flaws. And so this actually gets into our metrics in a little bit. We'll talk about how we addressed this. We noticed this problem in 2009, and we had to come up with a way to sort it out. And if you look at the scope of our test cases, just in general, we look at functions that are available on the underlying platform. So we're not looking at third-party libraries or frameworks. So in Java, we look at kind of the core Java APIs, but we don't look at struts or Hibernate or Spring or anything like that. In C and C++, we look at the C standard library. We have a little bit of stuff with the C++ standard library, just mostly in like string. We have a few test cases that use string types. We might expand that for 2011, some more C++ standard library, but we're not using Boost or any of the other kind of standard, not standard, but the commonly used C++ libraries. And the test cases are, they have some Windows-specific test cases, and then there's a bunch that are just kind of agnostic as far as they should basically work on any platform that has the standard C library. That's in C and C++. In Java, everything's pretty much the same anyway. But we don't have any test cases that are specific to non-Windows platforms, so Linux or Mac or anything. Part of the reason for that is we don't quite know how we would handle that, because then you'd have to potentially run some test cases on Windows and some on something else, and then figure out how to combine the results. And so it's a lot more complicated that way. When you get the test cases, the build scripts that we have are Windows specific. It's like batch files, and it uses the Microsoft Visual Studio compiler, the command line version. There's not like Visual Studio projects or anything. The test suite is too big, unfortunately, for that. But I know that NIST has looked a little bit at it, and we're going to be looking at making like make files or something to at least be able to build the platform independent test cases in Linux platform, for example. As I mentioned earlier, we don't have a lot of C++, and we might add some of that later. And as far as Java is concerned, we have servlets and we have regular Java application stuff. We don't have any applets or JSPs or anything. So that's kind of a limitation. We hope that at least the data that we have is at least indicative of kind of the relative quality of tools on JSPs and stuff. We do know that those are relatively common. This doesn't quite fit our test case architecture, is why we didn't include that. So this is some metadata about our test cases, just as far as the scope. As we mentioned, well, actually I haven't mentioned yet, but we have 60,000 or 59,000 test cases in total. Some of those are single file, some of them are a handful of files. So it ends up being like 80,000 source code files and 9.5 million lines of code, which is we're pretty proud of that number. Although I mean, like I said, we did automatically generate a lot of this stuff, so we have spent nowhere near the amount of effort that you'd expect to see that number. But and that's actually line, actual executable lines, so not comments or blank lines. And then look at CWEs, we cover 177, which actually sounds low because there's like 800 CWEs now, I think. But the reason for that is that CWE is actually kind of a forest where they've got different trees, and a lot of the CWEs are actually kind of more abstract flaw types higher up in the tree, so we don't cover those. We map our test cases to the leaves of the tree, basically. And so we think we do have a pretty good coverage of the ones that, again, are implementation issues that we can kind of fit into our test cases, as opposed to some CWEs are design issues that just we can't really represent in a test case. So the test cases are available on the NIST website. So if you go to this URL, you can pull them up, and it's also in the white paper and in our slides that are on your CD. They're known as the Juliet test suite. So there's 2 separate downloads, one for Java, one for C and C++. So please go check them out. And we really do solicit feedback on those. So we want to hear what people have to say about the test cases and how and what if they've got suggestions for things we should add, things we should fix, that sort of thing. Okay, so once we've, so I mentioned earlier, we run the test cases through our tools, we convert them into the CSV format. Now we have to figure out, okay, what's the true positives and false positives? And that's what we call scoring. So it's really a 3-step process. So the first step is we figure out what are the positives. So in what cases is the tool result associated with the test case that the tool result appears in? Because the way we've built our structure is we didn't make the assumption that we were going to fix we were going to have perfect test cases. We just kind of assumed that there would be some flaws that we didn't quite intend in the test cases. So what we do is in the format string vulnerability that we showed earlier, all we care about as far as tool results from that test case are tool results that have to do with format string vulnerability. So if a tool reports a null pointer dereference or a missing comment or who the heck knows what kind of a flaw type it might be, we just completely disregard it, because if it's not a format string report, then we're not going to care about it. So that's kind of the first phase of figuring out what are the positives. And then once you've done that, and that, like I said, that's all we care about. So everything else just gets thrown out, it doesn't kind of come into any of the later phases here. So once you've got your positives, then you can just simply look at the function name and say, if the tool was reporting it in the bad function, then it's a true positive. If it's in the good function, it's a false positive. So that's why we've structured the test cases the way we have, is to make this very easy. Like I said, it's in particular, we don't want to have to worry about which line number it appears on, because in some cases that may be actually kind of a range of lines, and also some of the test cases span multiple functions or multiple files. So you got to deal with, if the tool going to report the first function or the last function, well, all of them will have bad in the name. So then you can just kind of look very simply for that. And then the third phase is really just to go through and say, okay, now all the test cases where we haven't had a true positive, then we're going to add a false negative, because that way every test case is going to have either a true positive or a false negative, and that it kind of comes into our later kind of scoring statistic stuff. So now, once we had that, so we've got, as I mentioned, 39,000 or 59,000 test cases. So, and granted, you look at one language, but still, you've got thousands of test case results now that you've got to sort through. And we said, well, now we want to kind of boil this down into something interesting. Even at the CWE level, we've got 100 CWEs. No one's going to look through a report that has 100 different CWEs kind of broken down. So we created what's called weakness classes. We actually worked with MITRE when we were kind of first formulating this concept in 2009. So we kind of looked at grouping similar flaw types, and we did that by using CWEs into these 13 weakness classes. And so we said, let's put all the similar stuff together, so then we can kind of get down to this kind of countable number of things that we can talk about in such a way that people can make sense out of it. So these are the 13 weakness classes that we have defined. The one kind of variation is for Java, we don't have a buffer handling weakness class, because there are a couple issues that you could maybe call buffer handling for Java, but we just kind of lumped them into our unfortunately present miscellaneous weakness class. So, we tried to, like I said, group similar things together, but there are certain things that just didn't fit with anything else. So miscellaneous is kind of whatever was left over. So it's we had to at least do something in order to come up with this. But this chart just gives you kind of an example. CWE, the full list of CWEs is something we can provide if you're interested in that. So now that we had grouped our test cases into weakness classes, now we need to know, okay, now what values do we want to calculate over those weakness classes? Because just simply counting things is probably not what we want. We wanted to come up with some ratios. And so fortunately, we didn't have to make this up on our own. We're able to borrow concepts from information retrieval. So we've looked at precision, recall, and F-score, which we'll define in the next couple of slides. So precision is answering the question of what fraction of the tool results were correct. So basically, it's the complement of the false positive rate, one minus the false positive rate. But we spin it as the positive side. So what you would want is all these metrics that we talk about, you want the tools to be 1. So 1 is perfect, 0 is perfectly terrible, and the other tools all end up in between. Because you're taking the number of true positives divided by the total number of flaws, basically, or the total number of flaws that were reported by the tool. So the true positives plus false positives. And so your perfect tool is going to have 1, but in reality, most of the time, you're not going to see that. Although you will see that in certain weakness classes, you did occasionally see that you would see tools that had very good precision, usually accompanied by very low recall, which is the other metric of what basically flaws is the tool reporting. So this is what we feel is actually a much more interesting from our data, because this is something that's very hard to quantify if you don't have a very rigorous known answer test like we do. If you just kind of take a tool and run it on some open source code bases, you can get some notion for precision, because you can say it's reporting a bunch of stuff, which ones are false positives. You can get an idea for which tools maybe have more false positives or not based on some open source kind of stuff, or just running it on your own code base. But you really have no notion for what is the tool missing, because you have no idea what flaws are there. So this is basically the division. So the numerator is the number of true positives, and then the denominator is basically the number of flaws. So every test case is going to be either a true positive or a false negative. So that adds up to be the number of flaws there. And it's a couple other names that you could use on this. And then if you wanted to kind of boil those two numbers down into one number, then we use F-score, which is basically the harmonic mean of the precision and recall. And it gives you a way to kind of come up with one number to say, in general, how good is a tool over a particular set of data. And in particular, it combines the values in such a way that it tends towards the lower value. So just taking the arithmetic mean is not so good, because you can end up with a tool that looks a lot better than it really is, because it might have a precision of 1 and a recall of 0.01, because it only found one test case, but it didn't have a false positive in that test case. Then the arithmetic mean would be like 0.5, which is pretty decent in our study, whereas other tools may have had a much larger range of test recall. So they were catching a lot more flaw types, but they had more false positives because of that, and it gets, doesn't look quite compare properly. So the arithmetic mean is meant to, or the harmonic mean is meant to be kind of towards that lower value to basically, you want tools that are kind of equally good in both areas. So when we graph these, we make pictures like this that show the precision on one axis and the recall on the other axis. The background of this picture is actually shaded according to the F-score at each individual point. So what you would want in these type of pictures is you want the tools to be up here where the perfect tool is in the upper right. You don't want them to be down here where it's terrible. In reality, you kind of find the tools in the middle and in the upper left and lower right, because you'll see some tools that tend to favor reporting more issues, but having more false positives because of that. Maybe a little bit looser, algorithms, and then some that are more tight, where it's like they're only going to report the flaw if they're really sure it's there, so they'll have a better precision, but they're going to have less recall because of that, because they're missing more things. So this is the visualizations that we use. So we did run into a problem, as I mentioned, in 2009, where we noticed that there were two tools that were getting a recall of 1 and a precision of 0.5 on our test suite, and that was resulting in them getting an F-score of 0.67, which is actually decent on our study. And it didn't really reflect the fact that the tool reported every possible false positive, because there was really only one non-flaw and one flaw, maybe over a particular set of data, and the tool had lots of false positives, but that it didn't get reflected really in the fact that it's noisy in our data. So what we looked at is, what's another metric we could use that would maybe be more useful, and we came up with this notion of discrimination. So this is something we made up. We didn't steal this from anybody. But we certainly welcome feedback as to whether it's a good metric or not, but we feel that it is. Discrimination is a test case where the tool reports the flaw, but does not report any false positives. So it's a kind of a higher bar than just reporting the flaw. And every tool then on every test case is going to get either 0 or 1 discrimination. So you get a discrimination or you don't. So in some sense, you're kind of lumping together test cases where the tool didn't report the thing at all with test cases where it reported it but also reported the false positive. You're kind of throwing all of those out together. So discrimination is kind of a strong metric, I suppose, in that sense. And then once you've defined what discriminations are, it's very easy to calculate discrimination rate, which is, again, between 0 and 1. Just divide the number of discriminations by the number of flaws, and you get that. And you will find that the discrimination rate is always going to be less than or equal to your recall, because every true positive is going to count towards recall and it's going to count towards recall, but not necessarily towards discrimination rate. And both of those metrics have the same denominator, so that's how you end up with that. So then when we graph discrimination rate by itself, you can do graphs like this, but what we'll see in the next couple slides is we'll see some more interesting metrics. So now what you've all been waiting for, I'm sure. So again, if you have any feedback on our methodology, and please read our white paper, definitely let us know. We're interested in that. We're working in 2011 to improve things. But we do want to talk about the conclusions that we had from this study, and some of them actually mirrored what we found in 2009. So some things are the same, some things are changing. So we have basically, I think, 4 or so conclusions that we have. One in particular is that these tools are not interchangeable. So should be obvious that there might be better tools than others in certain areas, but we do get people sometimes that come to us and say, we want to buy a static analysis tool. We're just going to buy whatever one is cheapest or whatever one has the nicest sales brochure or whatever. And we really feel that that's an error, that the results on individual areas for different tools are going to be different, and we feel that you definitely need to look at the results as part of the overall kind of picking a tool. Of course, as I mentioned earlier, not the only factor to consider, but we do feel it's important. You can't just say, I'm going to get a static analysis tool, they're all the same. We also found that the tools perform differently on different languages. So a lot of the tools, as we saw in the earlier slide, covered both C, C++, and Java. But we saw that some tools did relatively well in certain areas on C and C++, and then did poorly in those same areas in Java, or vice versa. Sometimes you can even kind of tell where the tool came from, that the tool may have been originally kind of just covering one language and then expanded into other areas later, and you can tell they've got more limited results in the kind of newer languages that they've implemented. So in particular, that means that you can't take any of the data from our study, even this aggregate data that we really have, and draw any conclusions about any other languages. So sometimes people come to us and say, what tool should we use for C#? And it's like, C# is kind of like Java. They're both managed code languages. Maybe we can kind of extrapolate. And it's like, we just can't tell them that, because what we've seen is that it's really no indication at all of from our data as to probably just the same as flipping a coin. Yeah, the question was just, kind of what other languages the tools covered. Yeah, we didn't look at that. We only looked at these 2 languages and didn't look at any of the other capabilities. But no. So the other thing we did find is that complementary tools can be combined in ways that at least seem to make sense to us based on the results. So you can look at, there are certainly tools that are good in different areas, and you would say, let's use the buffer handling capabilities of tool A and the pointer and reference handling capabilities of tool B, and that'll give us kind of better coverage across different flaw types. And so we think that certainly makes sense from the results. Logistically, it doesn't always make sense of, are you really going to buy multiple tools and deploy them and have to maintain them and all that? We think it might make sense for certain projects that are really concerned about software assurance and want to get a wide variety of results, or maybe shops that are doing, more third-party assessment kind of stuff as opposed to a development team. But at least this is something that we found seemed to make sense from our results. We did find, though, however, that every tool that we studied failed to report a significant portion of the flaws. So of the 59,000 test cases, all of them had some issues. So the average tool in our study covered 8 of the 13 weakness classes. And so by covered, I mean reported at least 1 true positive in that test case, in that weakness class. So that means your typical tool for 5 of the weakness classes just did not cover it at all. Now, again, we have to caveat that result with the fact we were running these tools in the default configuration. So it could be that they cover those if you turn on the right switches in the configuration file or something. But at least in the default configuration, which is how we feel a lot of people are using these tools anyway, there is some limitations in the coverage in that sense. We also do caveat this with the fact that we had some open source tools thrown into the mix in our studies. So there are probably limitations on those as far as the kind of quality of the analysis. So you would assume that a commercial company with an R&D team is going to be able to do better analysis probably than an open source tool. So those might have dragged down some of these averages. And, but in the weakness classes that they covered, so of those 8 weakness classes, the average tool covered about 22% of the flaws. So that's the recall is 22.22. So that means that even in the weakness classes that they covered, there's 78% of the test cases that tool did not report the flaw in it. So some of that may have had to do with certain data or control flows that caused problems with the tool. Others just might have been particular flaw types that they covered. Again, we had some Windows-specific test cases, so maybe certain tools didn't do as well as on those as they would on general kind of C standard library stuff. But this is certainly an interesting result just in kind of looking at the overall state of the art. And what this basically tells us, as Chris mentioned earlier, is that these tools are not the silver bullet. These tools have limitations in what they're able to do. We feel that they're valuable for finding the sorts of things that they can find easily, and the fact that they're automatable and scalable is very important, but they're not going to solve all of your application security issues or software assurance issues. We also have some aggregate results here where we talk about these graphs here, the kind of picture, the pie, is all the set of test cases. So what we found is in C and C++, 25% of our test cases were not, there was no true positives from any of the tools. So there's 25% of the test cases that none of the tools were able to identify the flaw in. In Java, it was 46%, which is actually kind of surprising to me that it was that much larger in Java. So that's kind of one, I think, important thing looking at this chart is just kind of, again, looking at what the limitations are of these tools, what they're not finding. The other thing that's kind of surprising is that there's a very small overlap between the tools. So if you look at, where there's 6 or 7 tools, it's 0%, so they're not exactly 0, but they're close enough to 0 that they round to 0%. So there's very few things that are actually reported by all of these tools, which is kind of surprising because there's certain things that you would just expect that all the tools would find. Some kind of simple to find types of flaws, some, really common types of flaws that you would think people's, customers would be interested in. So that surprised us. Again, maybe this has something to do with the configuration that we're using in that, but it's still interesting to us. We also have a little bit of trending data between 2009 and 2010. So this is the same pie chart we just showed on the last slide. But we have a huge caveat on this trending data, and we debated a lot as to whether to even include this, but we feel it's interesting to look at. So we've got a wide variety of flaw types and data and control flows that we did in 2010. 2009, we had a much smaller study with a fewer number of test cases. We didn't have any of the data and control flow complexities, and we had fewer tools. But what we saw is that if you compare year to year, the kind of fraction of test cases that no tool found actually went down significantly, which is really surprising to me looking at the huge increase in the number of test cases. So there's a few reasons that might be. It might be because we just added test cases that actually were what the tools were finding. So maybe our small set in 2009 was not kind of representative of the overall tool performance. Maybe the tools are just actually getting better. We also did add some tools, so that may be reflecting that as well. And you also see in 2009 we had actually a fairly significant overlap in the 5 tool section. And then, like I said, even the 5 tools in 2010 is less than that. So that was a little bit surprising as well. And then in Java, we have kind of more of what you'd expect. So this is the Java chart. Again, we go from 6 tools back to 7 tools in 2009, much smaller set of test cases. But here you at least see things kind of moving in the direction we expected, which is the fraction of things that were not reported by any tools was 40% in 2009, went up to 46% in 2010. So it's increased slightly, which is kind of at least the direction we were expecting. Again, the overlap is kind of similar, I suppose. And then one other pie charts before we move into some other charts real quick. This is the discriminations that, the tools were. So again, the pie is the overall number of test cases. So 47% of your test cases, none of the tools were able to discriminate, meaning report the flaw without reporting any false positives. That's kind of surprising. What's really surprising me is the 85% over here on the Java side that it may have something to do with the nature of Java, because Java is always dynamically linked, and our test cases make some assumptions that we want tools to be doing whole program analysis, and maybe the tools just are choosing not to do that, or maybe we didn't have them configured right to do that sort of analysis. But so this definitely reflects kind of a limitation that we've seen in kind of the overall picture. But again, this is not to say that these tools are worthless because of this or that they shouldn't be used. It's that to reflect that these are not going to solve all of your problems, even on the things we're able to create test cases for. So these charts, I think, are probably more interesting because they're going to show you what, in the specific weakness classes, where the tools generally were strong and where they were weak. So if you're looking at deploying static analysis tools, if in C and C++ anyway, buffer handling, initialization, and shutdown, which includes like memory leaks and that sort of thing in C and C++, pointer and reference handling, your kind of typical null pointer dereferences. That's where you have the most discriminations and recall, I suppose. Recall is kind of high in the injection as well. But I should explain this chart, I suppose. The green is the discrimination rate. So that's the really good of the tool where they have discriminations. And then the gray is kind of like, well, the tool reported the flaw, but they also reported false positives in the test case. So it's good in the sense of coverage, but not so good in the sense of having false positives. So kind of depending on your appetite for dealing with false positives. So if you're someone who's, hey, I really want the tool to find lots of stuff and I'm willing to wade through some false positives, then you should basically read this chart looking at the tops of the graphs, the tops of the gray bar. If you're someone who's like, I don't want to deal with false positives, I just want to know what the tool is able to tell me without reporting false positives, then you would want to look kind of at the green bars here to see. And like I said, they're kind of similar anyway, other than injection, which is primarily format string vulnerabilities for C and C++, where you had pretty high recall, but not so great in the discrimination rate on average. But where the tools had problems was authentication and access control, information leaks, and encryption and randomness, which were all relatively small weakness classes. So, but still, it's a little bit surprising that these tools were not doing too well on those at all. Information leaks might have even been like none of their tools reported anything. Again, that's caveated with the configuration that we used in that. So but still, it gives you some idea of kind of what kind of problems these tools might be able to help you solve and what kind of problems in your software you're going to have to use other processes and things like that to address. So here is the kind of similar chart for Java, where we have, again, one less weakness class because buffer handling is not here anymore. But you'll see here information leaks is the highest in recall, but has a very small discrimination rate. So again, you got to kind of pick what type of work that you're interested in. But like pointer and reference handling is pretty good, and file handling is pretty good as far as discriminations. Miscellaneous, which I know is probably not helpful at all, I guess, because you don't really know what ended up in that weakness class. But the general idea you get of what's there. Number handling, it did not so well at all in this one. So and there's some other ones that are kind of low, but there's no ones that kind of stand out as clearly bad like you did see in the C and C++, where you had some that were just really tiny. And like I said, you can kind of compare the two if you want to flip back and forth and see. It's kind of interesting that certain classes go up and down depending on which language you're looking at, especially because you consider that 5 of the tools that we tested covered both languages. So I mean, there's some kind of randomness thrown in there because you've got some other tools, but there's a lot of kind of overlap. But the reality of it is that you almost have to treat a tool that covers multiple languages as separate tools anyway, because you don't really know what they're doing underneath the hood. It may be a completely different analysis engine that they just kind of market as one product. Okay, so last bit of conclusions before we wrap up. We did, as we mentioned, talk about, we studied some open source tools, and so we wanted to kind of do some comparison of, what do you get in an open source tool versus what you get in a commercial tool. And in particular, we have customers that come to us sometimes and say, I don't have any budget, what can I get with an open source tool? And of course, the big thing you're missing with open source tools is reporting capability, the ability to track things across builds. Some of them have some IDE integrations, but they're usually not that great. So there's lots of those other factors that go into when you're looking at open source tools. But we did want to look at just, again, looking at the results. How do the results compare? So the open source tool that we covered for C and C++ was very limited overall, honestly. It has a below average fraction of the flaws in every weakness class it covered. So it wasn't above average in any of them. And it also had an above average number of false positives in 5 of the 7 weakness classes. So I suppose it's not every single one of them, but it's, and I guess you can read out of that there's 7 weakness classes it covered. So that's not terrible, I guess, given that the average was 6 or 8, I guess, from our previous slide. But so we definitely say in the C and C++ world, if you really need a static analysis tool, you need to buy something. And in particular, the tool we looked at covers C and C++. I know there's a lot of open source tools that only cover C. We didn't look at those, but in general, our kind of experience is that they're kind of limited because they're doing kind of grep-like searches as opposed to any sort of data or control flow analysis. In Java, it's kind of a mixed result when you look at the 2 tools. So obviously, there's 2 tools now as opposed to 1, so you have a little bit more opportunity for things to happen. But in 3 of our weakness classes, an open source tool was actually the strongest of all the tools based on the F-score. So control flow management, error handling, code quality. Again, I think a lot of that, especially code quality and maybe even the other 2, is because the tool vendors for commercial products probably have a lot of those rules disabled by default. And so until you go on and turn on some of those code quality rules, they're not going to be there. Or they just don't have code quality rules because they don't think it's something that their customers care about. And that may be. And that's why, like I said, we don't look at overall results. We look at the results in the individual weakness classes. So if someone comes to us asking about static analysis tools and they say they don't care about code quality, then we can just kind of ignore those results in our data. So in 4 of the weakness classes, you had at least 1 open source tool, again, out of the 2, so you've got kind of 2 chances at it, was stronger than at least 1 of the commercial tools, and there's 5 different commercial tools. So it's kind of a, don't draw too much conclusions from that because it's a little bit of a weak statement, but it is at least interesting that you've got some capabilities that these open source tools are able to provide that are beyond what some of the commercial products are doing. And then in the 2 remaining weakness classes that the open source tools covered anyway, they were the weakest of all the tools. And then I guess in however many are left, the open source tools didn't cover them at all. So it's, like I said, it's very mixed results. I think just looking at the results, though, you can say that it's at least certainly better than the C and C++. But again, open source tools, you're going to be missing a lot of the other features that you really need in order to integrate these into your build process and development lifecycle and things like that. In particular, one of the big problems you'll have if you start kind of deploying these tools, you need to be able to know kind of what new vulnerabilities or bugs or flaw reports or whatever are being introduced as you're kind of going along, and the open source tools don't have any way to track that. So the really kind of way of kind of modeling what's been previously found and propagating those results forward and things like that the commercial products have are really a big feature that you need if you're going to really get adoption of these tools. Because the important thing is, if you buy these tools, you kind of buy into this notion, then you need to kind of adopt it and get the developers to actually use them and things like that. And so some of the things that maybe you start thinking about, well, do I really care about the ease of use in that? But I think it is important in actually getting people to use the tools. So now, just real briefly, as Chris said, we're going to try to end a little bit early. We're going to talk. Just one slide here really talking about our plans for 2011. So our plans are we're going to be updating, and actually we've started this already based on some feedback we've gotten, but we're continuing to get additional feedback. So if you look at our test cases and you say, hey, you guys screwed something up, you should add this type of flaw, you should add this type of control flow, data flow, whatever, definitely send us an email on our email address, cas@nsa.gov, and we'd love to hear from it and try to figure out how we can make the test cases better. And also our testing methodology, as I mentioned, is detailed in the white paper that we put on the CD. We'd love to hear feedback on that. We're getting input from vendors, in particular looking at configuring the tools this year, at least in the sense of making sure all the rules are enabled or turned on in the tools. We may do some other configurations as well. We're kind of debating where to draw the line of how much configuration we want to do. But we're also considering, we're probably going to add another 3 or 5 additional tools, and we're trying to kind of base that on which ones are most commonly used in the DoD and which ones have the kind of capabilities that we think are important to our customers. And we're going to start, by start we mean actually like running the tools on the test cases in October. So we got another couple months of doing some tweaking on the test cases and doing some other kind of changes. So with that, I'm going to give you this public service announcement that BlackHat told me to give, and we're going to wrap up. So I appreciate everyone for coming. Unfortunately, I don't want to take questions anymore right now, but we're happy to come up afterwards and you can talk to us offline. I just don't want to be on mic any longer than I have to be. So thank you everyone for coming.